Welcome you to the next session on embedded software testing. This is a lecture 11. This is the last session of this unit 1 of embedded software testing. Here we will go through the master test planning and its details, and in the end we will analyze the unit 1 details what we have studied so far. And in session 10 we have understood that different models, multiple we started with life cycle models, prototype and formal life cycles. Then we studied V model, having requirement design, implementation on the left hand side, and on the right hand side we have unit testing, integration and system testing. And we also went through the multiple V model life cycle, model, prototype, final product. These were considered for multiple V model life cycle. So we also went through the activities that are involved, techniques, test levels, types, other issues, the mapping to the multiple V model. We also studied a allocation of test related issues on the development cycle, and on the prototype and on the final product, how it is applicable for the multiple V model. Then we had gone through a nested multiple V model, which will be having multiple V models nested based on the components that we have. Usually in the larger systems we will use. And also we went through a couple of slides on testing by developers. That means at the initial stage of the testing by development team itself they can do it, since they have the necessary debugging and similar testing environment what is intended for testing, so that they can fix the errors or the bugs. We also went through why testing is important at the developer stage is in terms of finding the defects early to gain the confidence to go ahead with the next level, etc. Then we had gone through slide on testing by independent team. We know that all the tests are done independently by a separate team driven by them, including the test plan and all the stuff activities. So there are 5 stages of formal life cycle for independent testing: planning and control phase, preparation phase, specification phase, execution phase, and completion phase. And we had a exercise on that. Okay, we study about master test planning. What is master test planning? Typically testing of a larger system with many hardware components, hundreds of thousands of code, lines of code in the software, it behaves complex, right? That means it's a complex endeavor. So involving many people, specialists performing different testing tasks at various points in the project, very much required. And especially complexity in terms of the states, software states or the system states, and the transitions of certain components. Exhaustively we need to test it. It is something like a higher integration level or low integration level, that is based on the complexity that the system is involved, and the features, user friendliness, or business requirements, all these have to be considered as well in doing the testing. So what we do is we will have a dedicated teams. So remember here testing is done by a larger team. So larger team means we can further subdivide that larger team into sub teams, and some teams they can focus dedicatedly on performance requirements, specialized features, functionalities, low level requirements, etc. It can be segregated for the entire software testing. For these complex situations, master test planning is very much necessary. So what it does is it formulates a mechanism to control the overall testing process. So hence the master test planning has come into picture. It basically requires the complex systems requires a good plan. So that is why we need to have a master test plan. So that is why the term called master test plan. Okay, so larger system larger systems having complex functionalities and features have a high degree of attention to testing. Master test planning provides a mechanism to control the overall testing process for such complex systems. What it does is first the difference between the test types and the test levels is explained. So what are the test types? What are the test levels that we will see it in the next slides. So basically it will bring the differences between these two, because that is very much important in identifying the key elements of the plan. So that is why master test planning is conducted based on this. It is a difference between which aspects are being tested and which organizational entity is executing the test. The master test planning then deals with the combination of both. So what it primarily does is which or what aspects are being tested, that it will identify, and it will differentiate with who is doing the test or executing the test. That is what is organizational entity. This is nothing but a set of team or a set of allocated specialist or a person who will be involved for the entire testing activity. So they finally all this will be finally put together into the master plan. That is why it is very much required to have master test planning in order to test the complex systems. Complex systems, for example, I can quote something like brake control systems, engine control systems. We have flight control system, fuel measurement, fuel management. Don't assume that fuel measurement is just some sensor will be passed with the fuel and it will be measured against. There are a lot of control systems, control subsystems are involved, along with the sensors and their feedback, and there is something called I'll write it here, redundancy management. Redundancy management is something like we have quarterplex systems or duplex systems where one or the other channel, it could be second subsystem takes over for controlling the intended operations, or it could be one or the other systems which will be used in order to arrive at a specific decision. So that is where redundancy is very much important. So we have 2-channel system, 4-channel systems, etc., where almost each channels will have a similar functionality. Each channel's inputs are very much used to arrive at a decision which one is good, which one is bad, which can be discarded, which can be used. So typically in a flight control system, so when we have left wing, right wing, ailerons, or actuators. This kind of a redundancy is used very much. So definitely they live with the complexity of the underneath the software, hardware, whatever the subsystems that is involved within that embedded system. So to have a development life cycle or to draw a test execution, we need to definitely have a master test plan. So because it's a complex systems where we need to identify lot of activities, lot of types, uh, mechanisms or methods, etc. So that is why it is very important to have a master test plan. Okay. So what are the elements of master test plan? These are just basic elements what I am trying to highlight here. This can lead it to further or this can further broken up into minute details as we discussed in the earlier sessions about test planning, test cases, procedures, etc. Broader level test types are defined. That is the first thing of the master test planning. A test type is a group of activities with the aim of evaluating a system on a set of related quality attributes. That means test type identifies a evaluation mechanism for certain things, like it could be a performance, it could be meeting certain criteria, it could be a quality aspects in terms of coverage or standards, etc. So basically it does a it basically accumulates the group of various activities. Aim is to evaluate the system based on certain attributes or measures. Test types state what is going to be tested and what is not. So something like a scoping it does. The test types will define what will be tested, or what are the activities, how I am going to group it, and what are the tests that will not be taken care or that will not be done. So that is what the test types state about. It means a system can be tested from different points of view. It can be tested functionality, performance, uh, uh, business requirements, user friendliness, etc. So these are some of the quality attributes that describe the various aspects of system behavior. Of course, there are standards exist. For example, ISO 9126. I will just list out. So that will give the 9126, PO 178, etc. So some of these standards also can be used in terms of arriving at certain approaches for testing. So these are the quality attributes so that can be used for the test types. In practice, several quality attributes are often combined in a single test. That means a single test can have a single quality attributes likewise. And test types state what is going to be tested, what is not. For instance, a tester doing a functionality test is not. I mean, it will define basically who will do what functionality and performance related, or vice versa. The other way, like performance and the functionality in terms of which tester is going to do which one. The below table we can see some of the test types based on the applicability. So as I mentioned, applicability here means that it is again depending on the complexity of the underneath embedded system. So this table we have test type, its description, and quality attributes that are included. What are the test types that are considered for master test planning? They are functionality, interfaces, load and stress, support, it could be manual, production, recovery, regression, security, standards, resources. Okay, so let's see one by one. What is the functionality test type? Testing functionality behavior. That means the functionality is being addressed here. So all the features or the functionality of that embedded system will be categorized under a functionality test type. Basically, that is driven with the inputs. So input definitely will have error inputs to test the behavior of the particular functionality. And interfaces, as I said in earlier slides, basically it is an interaction between couple of subsystems or an external system or a signal or discrete, whatever it is. So that is what it does. Testing interaction with other systems. Other systems could be subsystem or any external entity. So this is coming under quality attribute called connectivity. Sometimes we can also mention as communication. So maybe communication is more sensible compared to others. Okay, so I mentioned it as communication as one of the quality attributes that we can attribute to interface. Then we have load and stress, allowing large quantities and numbers to be processed. That means we have a system capable of taking certain load, certain inputs, certain quantity of inputs, say 5000 RPM or 7000 RPM. So range is something like 1000 to 7000 RPM, let's say 7000 to 10,000 RPM, let's say, for example. Those kind of requirements or those kind of test type is coming under load and stress. So what we want to subject the embedded system is allowing the higher number with a fully loaded embedded system, so that we will test the behavior of that particular condition with the large number of inputs or large quantities when it is fully processed with these inputs. Okay. The next type is a support, providing the expected support in the system intended environment. That means the types, the test types, which will help us in terms of directly or indirectly arriving at some of the results. So it is the expected support in the system's intended environment, such as matching with the user manual procedure. So that means overall understanding of the some of the features or functionalities, behavior, to arrive at some analysis, conclusions, etc. All this will be part of this support testing. It is attributed as suitability. The next one is a production, test production procedures. That means we have a production environment. All the production based testing will be done under this procedure. So that will have a quality attribute in terms of operability and continuity. That means a embedded system should be able to operate with a minimal intervention or maximum automation, and it should continue the same way as it is expected once it is through with the given set of test procedures. Then we have the recovery, testing recovery and restart facilities. That means the like reboot, power up requirements, initialization, those kind of testing could be coming under this type of recovery, where we have a test recovery and restart facilities will help in doing this type of tests. This is listed under recovery quality characteristics. Then we have a regression. You all know what is regression testing, whether all the components function is correctly of the system has been changed. So why system will change? Because it could have been bug fixed or any upgrade would have happened or any testing failures to be able to reproduce, etc. So all this comes under regression. Regression can have any of these quality characteristics, that's why they have put as all. Then we have a security, testing security. So all security requirements, sometimes we can add safety requirements also under this test type called security. Then we have standards relating compliance to standards, like this much percentage of coverage should be there, complexity, coverage, etc. will all come under standards. So against the standards, these steps are defined. This also is categorized under security or safety because, for example, if you take aerospace projects, what happens is they call it as airborne safety. It means how the product is safe when it is subject to certain tests. So all those features come under these standards, and also it should be user friendly in terms of its operability and usefulness. Then we have based on the resources, uh, some of the subsystems that embedded system primarily can use, like power regulators, memory, communication interface, transceivers, etc. All these measuring equipments all are called as resources. So these resources type of testing can be under test type. Of course, you can combine with this also, interface as well as resources. You can broadly you can categorize this as communication. This again, as I said, it is subjective based on the complexity of the system. So these are some of the elements under test type element. Some of the test types that are listed. We can add more based on the need of the complexity that we have. We need to draw this because this is very important in terms of master test planning. The next one is test levels. The second element of the master test planning is test levels. A test level is a group of activities that is organized and managed as an entity. So test type is a group of activities with the aim of evaluating a system on a set of related quality attributes. Here we define the test types under the quality attributes what is going to be tested. In test levels, what we do is we list out a group of activities and how it is organized and managed as a set of activity is going to be defined. So the table below is some of the common test levels for embedded system subject to supply demand. Okay, so before that, and few words is that test activities are performed by different testers and teams. As I said, this because we are dealing with larger systems, so we may use different environments or various environments pertaining to certain set of features that is under test. So all these organizational aspects are the reason for introducing this test level. So that is why it is important to have a test level defined for master test planning. Test levels basically state who is going to perform the test and when. So it tells it states basically who is going to perform the testing and when it is going to be tested. The different test levels are related to the development life cycle of the system. It structures the testing process by applying principle of incremental testing. You know that incremental testing is with development process. We develop small pieces first. We integrate one by one, and then incrementally we build the system. When the various components are of satisfactory quality, they are integrated into larger components or subsystems. So likewise, we will develop the bigger systems. These in turn are then tested to check if they conform to higher level requirements. So we'll start with the small subsystems and components. Then we'll grow up with the higher incremental testing. Finally, we check if they conform to the higher level requirements. What is intended for that particular embedded systems. And we know that low level testing and high level testing. Low level testing focuses on isolated components executed early in the life cycle in the bottommost part of the V model. High level tests are tests on the integrated systems or subsystems executed later in the life cycle on the right hand side of the V model. It could be simulated or target based, etc. Based basically on the real life environment. So we'll go through the table of test levels. All of this we have gone through in our earlier slides in a different class sessions in this unit. We have detailed, but this is about master test planning, which defines each of those type of tests or levels of tests categorized under the master test planning. Okay. Hardware unit test, hardware integration test, model in the loop, software unit test, post or target based testing, software integration test, hardware software integration test, system test, acceptance test, field test. Again, these are all subject to applicability of the particular embedded systems. As we need, we will draw different levels pertaining to the embedded systems under test. Hardware unit test, which is test level is low, and it is done in the laboratory, in the lab, testing the behavior of the hardware component in isolation. As I said, it's a component level, unit level. It is called. You can also mention it as a unit test. Hardware integration test, that means it is also a low level. This will be done in laboratory. Testing the hardware connections and protocols. Basically, we have CAN, AFDX, Ethernet, whatever it is. All these are part of hardware integration, where we basically plug all the hardware subsystems underneath the basic embedded systems and we will test it. Then we have the model in the loop. This is categorized either as high and low depending on what are the type of models that we use. So we know that in the initial stage of the project we develop the models to prove it whether it is going to work. So basic purpose is proof of concept, testing control laws, design optimization. Some of the complex algorithms may need to be proven first before we actually develop and deploy. Of course, in terms of memory and performance, we may have to optimize. So in order to architect efficiently, we may have to do design optimization. All this will be covered under model in the loop, also called as MIL. Okay. The next type is software unit test, host or target based system. Of course, I told here is hardware unit test. Uh, Basically, different hardware components want to be tested, we can do it, or if it is not required, then we can go ahead with a pure software component test actually, because this gives a confidence that those units are fine. Because what will happen is while doing the software unit test on the particular unit, we may come across bugs or issues. So we presume that sometimes there could be hardware problem, there could be software problem, etc. To make it clear that we are good at hardware, we start with a hardware unit test. This can be done by a hardware team or a specialist who know about or who is knowledgeable enough on the hardware components. It is again a low level test. Laboratory plus host target processor is used. Of course, laboratory has both of this. Typically, it is used in the lab. Testing the behavior of the software component in isolation. Then we have the SIT, software integration test. It's also low level. It is done with the help of the target port connected to the host. We know that how the target is interfaced with IDE, then debugging environment, breakpoint, and all that. We will use it to do the integration. Basically, here we try to integrate the different software pieces within the system and integrate it. We will pass the parameters, test against those parameters whether the intended behavior of the flow could be control flow or data flow. That will be the aim of the test. The testing interaction between software components taken from the software integration test. Similarly, the next level of test is HSIT, where we focus on the system, the entire system behaving when it is integrated with different software components, and those software components how they have behaved on the target. The other one we focus only on the software to software the interactions. Here we focus on the software to hardware or hardware to software. Testing interaction between hardware and software is technically HSIT. Here also we use the same lab equipments, measurement equipments, and the target board with the simulation or whatever it is to prove that the software is working fine on the end system, end target system. Then we have the system test as an integrated unit, the embedded system unit, whether it works fine as expected is done with the help of this level called system test. It's a high level. Of course, the HSIT is also high level. Simulated real life. That means except few items, we will almost have the entire system. Say suppose exception is what? Simulated real life. That means it is not the actual system running on the field. Suppose if it is a fuel measurement, or if it is a speed, so we will not take the embedded system target onto the road with a high speed of 100 miles, 200 miles, etc. We will not do that. Instead, what we do is how it the speed or the fuel, actual fuel is going to fed into this. We are going to simulate those inputs, and those inputs with those help of those inputs, how it is behaving is what we are going to test it. So this is under system test, and aim is to test whether it is behaving as specified in the high level requirements. Basically, it deals with the HLR or SRS or SRD, is also called software requirement specifications, software requirement document, or high level requirement. A subset of high level specification is business requirements or user requirements. This is tested under acceptance test. That means whether that product can be accepted. This is also done with the help of simulated real life with the actual end target. So testing that the system fulfills its purpose for the user. That means basically we look from the customer or user perspective in all aspects of acceptance. And last category is again subjective. We can use the field test. Some of the complexity, some of the features need to be tested with the help of the environment, something like ambience or weather. Of course, weather also taken care, like we have a temperature chamber and all they will be doing, but as an integrated system sometimes we may have to test on the field. Those things are categorized under field test. Testing that the system keeps working under the real life conditions. The extreme conditions could be there, altitudes, whatever it is. All this will be taken care with the help of field test. So this is the test level under master test planning. So we have two types, test types, which deals with what is going to be tested and what is not going to be tested. So we will summarize all the group of activities basically to evaluate with the help of the quality attributes. Then we have the levels. All these attributes have been defined. How they are going to be tested. That means what level you are going to test it. Let's say modeling loop or software integration or hardware software integration, system test, etc. or a component test. All this will be considered for master test planning. So in continuation of the master test plan, here is a picture. We all know that we have understood already about this. Is another way of depicting master test plan. Don't get confused with what we have studied in our earlier session. It is same, where we have drawn a picture of different levels of test. We have acceptance test, system test, hardware software integration test, unit test, etc. It's all part of the master test plan. So a master test plan can be viewed as the combination of what has to be tested, it means test types, and who is going to perform those test activities or the test levels. So that is about the master test plan. Of course, we need to coordinate the various test levels. It should prevent redundancies and omissions. It ensures that a coherent overall test strategy will be implemented. Decisions must be made as to which test level is more suited to testing. Testing which system requirements, quality attributes, so that decisions have to be taken care. Of course, the specialized resources such as specialized test equipment, measuring equipment, and expertise to use that, all those have to be allocated to the various test levels of certain functionalities or features. Of course, there is a timeline or the agreed period that also need to be drawn inside the master test plan. So an overall test plan has to be drawn up, which defines the tasks, responsibilities, boundaries for each test level. It's very important to understand that boundaries in terms of expertise or limitation, etc. at each level of the testing methodology, which spans across this master test plan. So that is why this overall test plan is called master test plan. Basically, this is done by the project manager, and the project manager or it could be a test manager, depending on how it is organized in the master test plan. So he will delegate the above ones, all tasks, who is going to do what, all these responsibilities are done by the test management team or test managers or project managers. So overall he is responsible for this. So that is about master test planning, test level and test types. So three main areas of interest for the master test plan uh, that needs to be considered by project manager or test manager before he draws the master test plan. Test strategic choices, what to test and how it is, how thorough it should be. That is one of the important test strategy choice that has to be done. Allocation of resources, expertise. Resources could be from the material for the equipments one side, and resources could be from the human resources in terms of the expertise or uh, the experience that is required to be taken care, and how all these different entities for doing the test, the resources, the equipments, how they are going to be communicated. There could be involvement of a vendor also. Sometimes we may need to rent uh, uh, some of the power supplies or the measuring equipments. How we are going to communicate within these disciplines, that also is an interest for the master test plan. And of course the master test plan will know exactly what is expected from each of them and what level of support and resources they can expect. The master test plan serves as the basis for the detailed test plan for each test level. We can have a detailed test plan for each of the level. We can have a test plan for acceptance test. We can have a test plan for system test, integration test, unit test, etc. All this combined together, the master test plan is formed. It does not need to prescribe for each test level which activities must be performed in detail, but it can point to what can be done. That will be there in the detailed test plan. So whatever the details are stated. So the master test plan deals with decisions that concern areas where the various test levels can either help or hinder each other. So all these pointers will be part of the master test plan. Of course, there are other aspects in the master test plan also. Just list out just for the sake of listing it out. It is not mandatory, but for understanding sake, we'll do it. That is test strategy. We know that we need to have a test strategy and a team for the same. Infrastructure and organization. I would say who is going to do what. So this is basically some of the key elements of the master test plan. And we know that in TM method, all these above are drawn with the help of LITO principle. So what is LITO principle? Life cycle, infrastructure, techniques, and organization. So this all will form the master test plan. So master test planning activities. I will highlight a few points which are important. Formulate the assignment, global review and study. That means what is the strategy in terms of reviewing the outcome of the test, and how the team can start in terms of study. Determine the master test strategy. What is the basis on which the test strategy can be determined? Specify the infrastructure, define the organization, determine the global schedule. It means based on all these 5 above, the schedule is drawn in terms of using this and coming out with an execution plan for the same. So these are some of the activities. So this is done by a test manager, and he starts as an early activity in the development process itself as a overall test process. This is done by developing a master test plan, having a formulation of overall objectives, responsibilities for testing and defining the scope. Then a global analysis of the system to be tested and the development process is carried out. The next step is to use the information what is being discussed and carried out about how we can measure for taking the next step in terms of it could be a quality or performance, etc. Basically, we should have the aim of successful release of the system, having done with the complete testing. So this is the determination of the master test strategy and involves choosing what to do, what not to do, and how to realize. The test manager's main responsibility is to deliver this master test strategy. It accomplish this whatever we have discussed so far is getting accomplished with the help of master test plan. The required resources, infrastructure or personnel should be defined. To manage this, the communication between all involved disciplines and the required reporting must be defined. How the individuals are going to report and what frequency and to whom. All this will be part of the organization and the test plan. A good master test plan is not created in a quiet and isolated office. It is a highly what is that called, political task. I mean, it has a lot of buzz, a lot of people involvement and all that. Basically, it requires a discussion along with bargaining and persuasion throughout the organization. So that is a good master plan drawn by the project manager or the technical or test manager. So that is about the master test plan. The last part of the okay, so of the this session I am coming with a couple of slides just to bring some of the pointers which will highlight overall what we have studied in this unit in terms of principles. This is a good set done by Glenford JMIS. So I just want to point to this. So 10 principles of embedded software testing. A necessary part of a test case is a definition of the expected output or result. We know this. We need to have an expected output and result. A programmer should avoid attempting to test his or her own program. That means independency should be maintained. That means the programmer should always try to test as an independent guy, or he should not be biased while testing. A programming organization should not test its own programs. That means one is at the programmer level, another one is the organization. Thoroughly inspect the results of each test. That means once we have the results outcome, even though it is pass, we should have a justification or we should have a validation why it is pass. We should inspect it, we should watch it, we should make sure that the right results are achieved. Test cases must be written for input conditions that are invalid and unexpected, as well as for those that are valid and expected. So both have to be taken care of. Examining a program to see if it does not what it is supposed to do is only half the battle. The other half is seeing whether the program does what it is not supposed to do. So that's both of them are very important. First we will do what it is supposed to do. The example telephone instrument, what it is supposed to do, and the same telephone instrument is what it is not supposed to do when something is not required or something is not specified in the specification. Seventh principle: avoid throwaway test cases unless the program is totally throwaway program. So unwanted things we should analyze properly before we make it unavailable or unwanted. Do not plan a testing effort under the tacit assumption that no errors will be found. So we should not waste having testing effort just for the heck of putting some effort. We should have appropriate effort for achieving the success of the test. It could be 100% at one go, or it could have some errors, but effort should be there always, and effort should be on the right direction. The probability of the existence of more errors in a section of a program is proportional to the number of errors already found in that section. This is a very interesting principle. Is always proven. I have seen this, and I am for this actually. Basically, why? Because I have a source code of say 1000 lines, and I found say some 20 bugs initially, and at the end of the test of this 1000 lines, I found say 100 bugs. Definitely, those 80 bugs could be based on the 20 bugs which I found it in the initial stage. So there is a proportionality that already found errors could result in more errors of the new errors or more errors that could be unearthed. Testing is an extremely creative and intellectually challenging task. That means uh, testing is equally important and equally well rewarded task considered in the industry. So that is about the 10 principles of embedded software testing. We have alpha beta. This is basically need not be part of the embedded software testing, but some production environment this is being used, especially on the application side. But I've heard that alpha and beta testing are also used in some of the embedded systems production environment. So just to understand what it is, typically used in production, the focus of the testing is to simulate the real users by using a black box and white box techniques. Alpha test done by the customer alpha test at developer side by customer. Means customer will have an idea of the product at the development side. So developer looking over the shoulder, recording errors, usage problems, etc. All this from development perspective is taken as alpha test. Controlled environment. It means still it is not a full-fledged or released environment with certain conditions that is carried out. So the next type of test after the alpha test is beta test at one or more customer sites by end user. That means the end user, the real user of that, will be testing the product at the customer site, and there is no developer involved for beta testing. It's something like a live situation where the product is on the market or the field. Developer will not have any control. Only he'll be reported of the issues that is coming out of this beta test. Customer records problems, real or imagined, and reports to the developer. So that is about alpha and beta testing. There are a few differences between that. Alpha testing performed by testers who are usually internal employees of the organization. Beta testing is performed by clients or the end users who are not employees. It is on the field. Alpha testing performed at developer side. Beta testing is performed at client location or end user. He himself can have the product and test before he uses actually for his need. Reliability and security testing are not performed usually. This may not be applicable for embedded system, but in general, this is how they are using it. Reliability, security, robustness are checked during beta testing. Alpha testing involves both the white box and black box techniques. Beta testing typically uses black box at a system level. Alpha testing requires a lab environment or test environment. Beta testing doesn't require any in-house environment or testing environment. Software is made available to the public or the end user and is said to be real-time environment. Long execution cycle may be required for alpha testing. Only few weeks of execution is required for beta testing. Critical issues or fixes can be addressed by developers immediately in alpha testing. Most of the issues or feedback is collected from beta testing will be implemented in future versions of the product. So alpha testing we have still a chance of reverting back with updates of the product, whereas beta testing it has to go through a different chain of implementation and versions. It has to bring back to the factory and all that. Alpha testing is to ensure the quality of the product before moving to beta testing. Beta testing also concentrates on quality but gathers user inputs on the product and ensure that the product is ready for the real time users. So why I have covered alpha and beta is some embedded systems can be covered under this. This is basically they use in industries like telecom where they have OSs like Android or Google. So they release alpha test released products and given to the customers, group of set of customers who will use it in the real time environment. And that type of testing is called beta testing at the customer side. Of course, end of session we have words. It's a repetition of all that. So maybe we can add some of the items from this class, something like schedule in the strategies there. Strategy or competitive strategy, both are same. Any other words which you want to look at? Master test plan, of course, is part of a test plan. We all know that. I think one word is model in the loop. So this is important. It's also called as MIL. And we will also see the master test plan. Master test plan. Okay. model in low. We have SIT, HSIT, hardware software integration, software integration. Okay, the last part is the question. What are the main elements of master test plan? List the principles of embedded software testing and their importance. And maybe we can have another question on beta testing. List out the differences. Okay, so with that we will conclude this session. In the next session we will take up the next unit of embedded software testing. Maybe I will recap of all the sessions that we had for some duration to begin with. The 11 sessions we had in the first unit. Then we will take up the second unit on testing methods, dynamic testing, model based testing, coverage testing, etc. as part of the next session. Okay, thank you.